Okay, friends, let's just do a quick recap of the types of problems that you can do with these normal distributions, these bell curves, if you will. The first one we looked at anyway, was if you start with a raw score. I've been calling those X for random variables. So the first thing you have to do is you want to use that formula that we kind of derived today, and you want to convert that raw score, which I'm calling X, to a Z-score. And if you've got more than one raw score, you'll have to convert each one of those to a corresponding Z-score. Once you've got your Z-score or your Z-scores, you're going to use our calculator to find the area that corresponds to it. So I took a quick little screen grab of the calculator there. That's the part you want to use for this kind of problem, that part right there. So that's if you start with a raw score. That is the first kind of problem you can do with a normal distribution. But there are other kinds of problems you can do. For example, we've seen ones where you actually start with the area. Okay, so if you start with an area, the first thing you want to do is actually start in the calculator, because you need to find the Z-score or scores, depending on how many you need, that go along with that area. Make sure that when you put the area in, it's in a decimal, okay? And then the calculator will know if you need two based on the selection that you use in the buttons. And then all you got to do is use our good buddy formula that we derived earlier to convert the Z-score into a raw score. There you go. Let's look at a couple more problems just to kind of learn to identify what type we're looking at. And one of the examples I like to use is actually human pregnancy. Not surprisingly, there isn't 100% consensus with how long a pregnancy is, but there's enough published data out there based on studies of thousands of women that I think this average of 266 days and a standard deviation of 16 days is good enough to get us in the ballpark. So just like we did with baby weights, I want to look at the short pregnancies like we looked at the late babies. So how do we identify preemie births, premature births? Well, I've seen it done a number of different ways. Here's one way of doing it. The 5th percentile is the cutoff for premature births. If you think about it, it's similar to the 5th percentile was the cutoff for underweight babies. But the question I have is, if the 5th percentile is the cutoff for premature births, when is that? 266 days is 38 weeks. So how many weeks is this premature cutoff? Well, let's go figure it out. Okay, friends, we're back in our Excel calculator, which is going to do the heavy lifting for us. We just got to figure out whether we're at the top or the bottom. And hopefully you recognize we're in the bottom. We have the area. We need to cut off those shortest 5%. So I'm going to change my area to 5%. And I'm going to do area left, because those are the babies. Those are the preemies right there. Now, that Z-score should look familiar to you, right? It should, because it's the same. It doesn't matter what context we're in. If it's a bell-shaped distribution, the bottom 5% will be chopped off by a Z-score of negative 1.645. All we got to do now is convert that back to a corresponding raw score using the average and the standard deviation. Let's do that next. Okay, so we know that preemie babies, by this definition, are those that are 1.645 standard deviations below average or further. There's a whole slew. 5% of babies are no closer to average than this. But that doesn't help us with telling a mother, like, how long does your pregnancy need to be until you're not in the preemie range. So we got to convert this to the raw score, give it some context, because this is context-less. There's no weeks or days or months in this. It's just a number of standard deviations. So that's where the good old formula we derived in the last few videos comes in handy. Okay? So we got to take the average, then add to it the Z-score times the value of the standard deviation in the population. So now we know all three of these things. We know the average is 266 days. We know that is a negative 1.645. And we know the standard deviation 16 days. And if we crunch all this together, I did it on Google, I got 240 days. Which is just about, was that 35 weeks? 34 weeks. Just a little bit above 34 weeks. So there's your cutoff. There's your cutoff for preemie babies. Any baby born before about 34 weeks, under this definition of premature, is considered a preemie baby. Make sense so far? Okay, let's look at another one. All right, so those were the short pregnancies. Let's look at the long ones. Let's look at the pregnancies that are so long that they're induced. So here's another definition I've seen for when it's time to induce labor. If an expectant mother has exceeded her due date by 2 weeks. What's the chance that a pregnancy will last more than 2 weeks past the due date?
Okay, so for this one, we're finding the extra long pregnancies, or at least the long pregnancies, longer than average. 14 days, 2 weeks. So that's about 40 weeks, right? Yeah. So I guess what we have to figure out is 14 days. That's if the average is 266, 14, that's 280 days. We have to figure out what percentage of pregnancies are 280 days or longer. Now, it's a little bit of a trick question, right? Because according to this definition, if they hit 280 days, they're getting induced. But that doesn't mean the pregnancy couldn't naturally want to go longer. Remember, they're bell-shaped. Some might be biologically predisposed to go longer, but by this definition of induced labor, they won't get there because they'll get birthed at 280 days. So what kind of problem is this? Is this a bottom of the spreadsheet problem like the last one, or a top of the spreadsheet problem? Well, let's think. The last one we did was a bottom of the spreadsheet problem because we had the percentage in the beginning. We were told we're looking for the shortest 5% of pregnancies. This one, we don't have that, do we? Actually, we've got a number of days. We've got context. That means we have to use the top sheet, which means we have to have a z-score, which means we got to convert this to a z-score. Yes, yes. So we've got to turn a raw score, this is a raw score, into a z-score. So we're going to use the first formula we derived today, which is this puppy dog right here. And we just got to run our values through it. We know the raw score is 280 days. Minus the average, which was the 266 days. I'm running out of space here. I apologize. I probably could have left the days off, but I want you to see what happens here. Standard deviation, plus or minus 16 days. Now we do the math. 280 minus 266, that's 14 days, which is 2 weeks. We knew that anyway. 14 days divided by 16 days. Oh, look at that. Just like we've done in Math 98 and Math 105, dimensional analysis for the win. I grab my colored chalk, divide off the units, and you're left with 14 sixteenths, or 7 eighths, or whatever you want to call that. What was that, 0.875? 0.875 what? Standard deviations above average. So in other words, any pregnancy that's 0.875 standard deviations above average is going to be induced. What percent of them are there? I don't know. That's why I built you the calculator. Let's go take a look.
Okay, my friends, so we're going to be in the top part of the sheet. We have our z-score. It is 7/8 of a standard deviation. We do not need the second one. We only have the top one, and we want to be above that z-score. And there we go. Those are the pregnancies that are going to be induced. And look at that percentage. I remember the first time I cranked this number, I was really surprised by that percentage. That's very high. That's almost 20%, which would be 1 out of 5 pregnancies are going to be induced. And that, to me, seemed exceptionally high. When I teach this in class, I often get great discussion around my numbers and how they might not be right. And I admit it. This is based on the research that I've done. As a matter of fact, in the homework that you'll look at after these videos, we're going to mess around with some different assumptions about the length and, most importantly, standard deviation around that length of pregnancy, and see how these numbers can actually look different depending on what you're assuming average is. But I think we've got a good enough start to really put the normal distribution to use. The last 2 videos in this playlist, as I mentioned before, are purely optional. They are if you want to see why the area in the entire normal distribution is indeed 100%. You don't have to be interested in that at all. They're slightly older videos. I recorded them like 4 or 5 years ago. I still look like an old man, but watch them if you want to. Otherwise, jump into the homework and give it a shot.